Hey guys, welcome back to this series of tutorial on electrical network design. If you haven't yet subscribed to CMTEQ channel, please consider doing so to never miss tutorial like this. This is tutorial number 4 on this series of tutorial. In this tutorial, we're going to focus on how to calculate the fault current, the potential fault current that might flow on this bus bar in case of a short circuit. Now, that is the main reason that we calculated the per unit values, because precisely they're going to help us determine what will be the magnitude of the fault current. Now, when we talk about the prospective fault current, is the magnitude of the fault current that might flow at any point in a circuit in case of a short circuit. So the purpose of this tutorial is precisely to determine the magnitude of the fault current on each one of these bus bars. That way, the design engineer that is designing the network will know exactly what kind of equipment and the rating to place to protect this bus bar and the equipment that it will be supplying in case of a short circuit. Because if the short circuit occurs because of someone accidentally touching the live pad, you want to protect that person as quickly as possible. Or if it's a faulty equipment, you want the equipment also to be protected to minimize the cost of repair. Okay, now as we may know from the simple principle of Ohm law, the current depends on the resistance of the path the current is taking. So for a higher resistance, the current will be small. Now, the per unit value here, which was an impedance that we have converted back to a per unit value. If you look at the past videos, you'll see how we did that. So this per unit value will represent almost a resistance to the current flowing. This is why we're going to use it to determine our fault current that's going to be flowing to bus bar 2. But before, the fault current at bus bar 1 will solely depend on what the generator is supplying. Now the generator here, I've explained it already on the previous tutorial. The 0.24 is like an internal impedance, an internal resistance of either the battery or any power supplying device. Now, these internal resistance determine what is the maximum power that the device must deliver. So in electronics design, for instance, if you are designing a power supply, you have to make sure that the overall impedance of your supply is low so that there is maximum power transfer. Because if your impedance, your internal resistance is high, you're not going to have maximum power transfer. There will be losses due to the internal resistance, because whenever you want to pass a current from point A to point B, you know the current is going to have to pass through this point here. And the maximum current that's going to get from A to B depends on what happened here. Now this is almost like your battery. Now this is the internal part of your battery. Now to ensure maximum power transfer from A to B, you have to make sure that there is less resistance inside here so that you can get all the power to B. This is why it is important for your power supply or your battery to have an internal resistance that is almost negligible or that is very low. This is why you have this per unit here, which represent an internal resistance of the generator is very low. This means then that per unit value will determine how much current we're getting at that bus bar 1. Now let's see how much current we're going to get into bus bar 1 from that per unit value. As we have said, 0.24 J per unit is the generator internal impedance. Then we use a common formula that is used to determine the per unit current. Remember, on the previous tutorial we've said I per unit is equal to 1 over Z per unit, 1 being represented by the 1 volt per unit because in the per unit system, as the names implies, unit, so we are dealing with one only. That's why everything is represented in a percentage value that must be below 1. That's why it's called per unit. So moving on, as we already said, 0.24J is the internal per unit of the generator, and using the per unit formula for the current, I per unit is equal to 1 over 0.24 with an angle of 90 degrees. Now this is the formula to calculate the per unit current. The 1 here represents the 1 volt per unit. Please look at the previous tutorial where we introduced that formula. This gives us a current of 4.166 amp. Now that is the per unit current. This is not the short circuit current. This is the per unit current in terms of percentage from a 1 volt per unit perspective. In order for us to get the short circuit current, we need now to multiply the I per unit times the I line, which is the base current. Now the base current is the current. Now if this is a 3-phase generator, the generator must have 3 phases here. So each phase is bringing in a current into the busbar here. That's what we call the line current or the base current. Now to find that current, we use this formula that is on your screen. So we replace the value, then we get the current of 437.386 amp. That is our line current. As we've already said, to get our short circuit current, we need now to multiply the I per unit times the I line. And that gives us 4.166 times 437.386. It gives us about 1.8 kiloamps of current. Now this is the maximum short circuit current that's flowing in this busbar. So from the generator to this busbar down to earth, there will be a 1.8 kiloamps of current. Now if you drink too much red wine and you think you can go touch that busbar, remember there will be 1.8 kiloamps of current with a potential of 132 kilovolt flowing from your hand through your heart down to earth. And you don't want to know what will happen to you. Please don't do that. Now moving on, we may also calculate the short circuit MVA. Using our short circuit current, we can then calculate the short circuit MVA, which gives us a 416.6 megavolt ampere. Now you'll notice that this is the MVA. Remember, this is the base MVA, so that's the total power the generator is supplying in this case. Now if we take this line current here, we replace it in this formula, we should be able to get the same 100 MVA. Now to calculate the short circuit MVA, we now use the short circuit current into this formula to get the value of the magnitude of the short circuit MVA. Now moving on to busbar 2. Busbar 2, we're going to follow the same process. The process is of calculating the total impedance that is on the path to where the current is flowing. Now the current is now going to be flowing from the generator down to this busbar, down to the line 1 and to this busbar here. So we want to know what is the magnitude of the short circuit current on this busbar. Just like we have explained, the generator acts like an internal impedance of a battery. Now to move power from point A to point B, you need to ensure that between A and B you have minimum resistance, so that your maximum power on the input will be maximum power on the output. This basically means we need to add the internal impedance of the generator plus the per unit here of the line, and these together will be the Z per unit total that will determine how much per unit current we're going to get for the system. So let's see how it works. the total per unit impedance from generator to busbar 2, that is from generator 1 to busbar 2, will be Z per unit of the generator is 0.24. Z per unit of the line is equal to 0.011 with an angle of 73.82 degree J per unit. This is a polar form. We convert it to the rectangular form. That way it will be much easier to add it with this one. We may also convert this to polar form and then we add it together with the polar form impedance of the line there. Moving on, the total Z per unit flowing from the generator to line 1 will then be equal to this, and that gives us a total Z per unit of 0.251 with an angle of 89.3 degree. Now we're going to use this Z per unit total to determine what will be our I per unit. The I line will remain exactly the same. It doesn't change because we still have the same line that's running from the 132 kilovolt. So imagine if we're working from one single phase, we will have exactly the same phase running on the transmission line. This is why our I line will not change. Then we calculate our I per unit, which is now 1 over Z per unit. Now Z per unit is now this total Z per unit that we found of J024 plus this one, so that it gives us 3.984 amp. That's the I per unit. Just like we've done here, we now need to multiply the I per unit times the I line. We're gonna do exactly the same thing there. So I per unit times I line does give us the short circuit value of 1.742 kiloamps. So that is the maximum short circuit current that is flowing at this point, busbar 2. Okay, now we may also calculate the short circuit MVA from the same busbar, and that will be about 398.4 megavolt ampere. That is, we use the same process that we've done here to determine this one. We do exactly the same. Instead of using the line current, we now use the short circuit current here, and we found this. So we're going to stop this video for now here before it gets too long. In the next tutorial, we're going to do busbar 3, busbar 4, and busbar 5 to close the tutorial part 2. So please stay tuned and don't forget to give it a thumbs up and subscribe to my channel for future tutorial like this. Thank you.